In this problem, it says that a road is to be built between two cities, C1 and C2, which are on opposite sides of a river of uniform width r. C1 is A units from the river, so that's this distance, and C2 is B units from the river, so that's this distance, and A is less than or equal to B. A bridge will carry the traffic across the river. Where should the bridge be located in order to minimize the total distance between the cities? So we want to give a general solution using the constants A, B, P, and R as given in the picture. So P is the distance between the cities, the horizontal distance there. And so what I've done is I've taken these triangles from the figure and I've reproduced them down here. So D1 is going to be our first distance that we calculate. And I'm going to use Pythagorean Theorem for that. So D1 is going to be the square root of A squared plus P minus X squared. And then D2 is the square root of B squared plus X squared. So our total distance is going to be D1 plus R plus D2. So that is the square root of A squared plus P minus X squared plus R plus the square root of B squared plus X squared. So that would be D. Okay, now we want to minimize D of X, and so it asks us to find the derivative, D prime of X. So I've written down D of X. I want to calculate D prime. And remember the square root, let's see if I can do this. I can actually just make this, all of this raised to the 1/2 power. So when I take the derivative, it's 1/2 A squared plus P minus X squared to the negative 1/2 times the derivative of the inside. A squared is a constant, so the derivative is 0. So I need to take the derivative of P minus X squared, and that's going to be 2 times P minus X to the 1 power times the derivative of the inside. P is a constant, so that derivative is 0, and the derivative of negative X is negative 1. Okay. Now I'm going to take the derivative of R, and that's a constant, so that's 0. And then finally the derivative of the square root of B squared plus X squared. I'm going to do the same thing here, 1/2 B squared plus X squared to the negative 1/2 power times the derivative of the inside. B squared is a constant, so the derivative of the inside is just 2x. Okay, so let's clean this up and then set it equal to 0. Oh, well, let's see. We'll just clean it up and that'll be the answer to this part. All right, so what can I do? 1/2 and the 2 cancel, and I have a negative 1 times the P minus X in the numerator, and then in the denominator I have the square root of A squared plus P minus X squared plus the 1/2 and the 2 cancel, and I have X over the square root of B squared plus X squared. And so I'm looking for that, and that looks like C. Okay, so that was actually A. I missed out on that, so that's plus the B squared plus X squared, not minus. Okay, so we've got our derivative, and now we're going to take that derivative and set it equal to 0. So I want to solve this for X. To solve this for X, I'm going to add the first term over to the other side so that I end up with X over the square root of B squared plus X squared equals P minus X over the square root of A squared plus P minus X squared. And now I can cross multiply, and I have X times the square root of A squared plus P minus X squared equals P minus X times the square root of B squared plus X squared. So at this point, there's not a whole lot we can do because of the radicals. So what I'm going to do is I'm going to square both sides. And that gives me x squared times a squared plus p minus x squared. So the square cancels out that radical, and then the x is, of course, squared. And then we have p minus x squared times b squared plus x squared. Okay. So now I'm going to distribute the x squared on the left side, and I have a squared x squared plus x squared times p minus x squared. And on the right-hand side, I'm going to distribute the p minus x squared. So that gives me b squared times p minus x squared plus x squared times p minus x squared. Now notice, very beautifully, x squared times p minus x squared is the same on both sides, so we can lose those. And that helps a lot, because now I have a squared x squared equals b squared times p minus x squared. And now, since everything is squared, I can take the square root of both sides, and I have ax equals b times p minus x. So ax equals bp minus bx. I'm going to add that bx term to both sides, and I have a plus b times x equals bp, and I divide both sides by a plus b, and cha-ching, there is my solution. So x is equal to bp over a plus b. And then in the final question, they ask, is there any values of x for which the first derivative does not exist? And so when we look at the denominator here, is there any value of x which would make this denominator 0? And there isn't, because this has to be a positive. The worst we can do is say x is equal to p. That's going to make this part 0, but we still have the square root of a squared, so that's a positive value. And the same thing over here. Worst thing for x is that it could be 0, and then we still have a positive denominator over there. So there's no values for which the first derivative does not exist. So that's the end of that problem.